one more time for being with us. This was a fascinating case. I'm sure it was inspiring for many people. We are going to do a transition now. So thank you once again. Yep. All right, so we are going to transition to our next and last speaker, Mr. Greg Hutto. Mr. Hutto is wing operations analyst for the 96th Test Wing, and he is responsible for embedding designed experiments as the principal test method for several hundred tests each year. He teaches an extensive series of short courses and test methods to all testers in the wing, from the wing commander to our 520 scientists and engineers. As a lieutenant colonel in the U.S. Air Force Reserves, he served as senior military advisor to the Air Force Operational Test and Evaluation Center Test Support Director, and as special advisor for test design to the Air Force Flight Test Center commander at Edwards Air Force Base. Mr. Hutto is a distinguished graduate of the U.S. Naval Academy in Operations Research and holds a master's from Stanford University. Over the past 30 years, he has served in nearly every branch of test and evaluation, from laboratory basic science to joint operational field testing. And Mr. Hutto would like to publicly repent of his 11 years of testing without the benefits of the principles of well-designed experiments. So thank you, Greg. I would like to throw it over to you. We see your slides, so you are good to go.
Boy, that's great. Thank you so much for the opportunity to speak before this summit. It's always a great opportunity to collaborate with Stat-Ease, one of my absolute favorite companies to work with. Your customer support is superb, and as you'll see, I'm a big fan of your software as well. Jay, I wanted to thank you for that talk. I learned a couple of new things, which was always great after doing this for 30 years or so. And I think if I get a chance to speak next year, I'm going to talk about my experiences in changing the way organizations do business. That is the hard problem. The statistics and experimental design is easy. Changing people's behavior is extremely difficult. So today, I'm going to talk about a particular technical problem that is of great interest and import, not only to the United States Air Force, but to all of our military services. And it's just gnarly. It's a very difficult problem. I've been banging my head against the wall on this since about literally 2004. And in the last 4 or 5 years, we've had some big breakthroughs, both in the design side and the analysis. And so without further ado, let me get on. Sherry, thanks for the intro there. I'm certainly proud of my family. My children both make their living in the air. My daughter serves martinis as a flight attendant, and my son, returning from his third combat tour as a Strike Eagle bombardier navigator, he uses these tools I'm talking about today every day. So I've got some skin in the game. And then, of course, I've got my wonderful wife, Dr. Deb. She's far more educated than I am and helps me out in a lot of my work. All right, so there's our abstract. Here's what I'm going to talk about. Just a couple of minutes about who we are and where we're coming from. I'll introduce the problem of accurate target coordinates, and then some of the difficulties we face with design and analysis. Today, we're really going to talk only about the design, but the analysis is also poses a lot of difficulties. And then I always enjoy listening to Mark Anderson and the fun that he has with practical physics-based experiments. And I'm with Jay that practical experience with experimental design is really a great sales feature and really enhances the learning. And so in the spirit of what Mark offered us at the beginning of this, I'm going to offer at the end, we actually have an experiment you can try at home to solve this problem yourself. And then we'll have a summary and take some questions. All right, so this is us. Let me see if I can get my laser pointer working. There it is. All right, so this multicolored area, this is our 800 square miles of land ranges. That little red triangle, which is an Air Force symbol for a target, maybe not a good idea, but that's where I live, actually, right on the edge of one of these ranges here. We test all kinds of things here at Eglin Air Force Base. All of the, basically almost all the platforms, all the weapons that we use, a lot of our communications and navigation systems. We do the networks and the data links that string us all together. We're developing this 125,000 square mile range over the eastern Gulf of Mexico. When you hear about drilling in the Gulf, they're talking about taking away our range because most oil platforms consider it an unfriendly act to drop bombs on them. So there's no oil drilling over here. It's all over toward Louisiana, and we're hoping to keep it that way. There's our CV-22 tilt rotor aircraft, and we just started testing a whole series of these electronic vertical takeoff and landing systems, e-VTOL systems for their possible applications to military problems. So lots and lots and lots of interesting things. Here's a sniper targeting pod. This is a really high-tech $1 million camera with a laser on board, and that's going to be the focus of a lot of what we talk about today. And we're recruiting, so if you'd like to come live here in the world's most beautiful beaches and very reasonable cost of living, and you're interested in doing experimental design, get a hold of me. All right, Air Force does ops research pretty well. I've been a ops researcher in the Air Force for 43 years now. Military and active and reserves, contractor and government civil servant, and I'm proud to say we won the basically the Nobel Prize in Operations Research, the world's best OR organization from our Daddy Rabbit Professional Society, Informs. We won that in 2017, and I'm also pleased to say that it was our work in experimental design that was one of the 3 proof cases that we use to illustrate how well we do operations research. So very proud of our Air Force and the OR work that we do. All right, but good news is it all started with beer. I love the history of experimental design. You can date it certainly back to many of the alchemists and experimenters in the Middle Ages, but it really started moving at the Guinness Brewery in the 1890s when the original one of the Guinness family, Cecil Guinness, decided to take brewing from an art to a science. And so he hired the best chemists and mathematicians that he could find. One of those from Oxford was William Seeley Gossett. And what they did was they took these young mathematicians and chemists, taught them the science of brewing as they knew it. And then after a couple of years as assistant brewmasters, they gave them their own microbreweries and set them to work in making better Guinness. And so William Seeley Gossett, being a very practical man, wondered, how large a sample do I need to compare a new formulation against the old formulation and be able to declare that this was in fact better, and not make one of those mistakes that we're so prone to, saying it's better when it's not, or failing to find a better one when it is. And so he went around and asked lots and lots of folks, including the preeminent statistician Carl Pearson at the time. And Pearson said, we'll take thousands of samples. And Gossett went away sad, because that's not a practical answer to his problem. And so he sat down and did basically a bootstrap by hand by writing the numbers from a particular set of 3,000 measurements of criminal criminal height measurements on pieces of cardboard in samples of 4 and formed the mean versus standard deviation of those samples and bootstrapped small samples of those 4 at a time and plotted the distribution. And what he found was he had a normal distribution with fat tails, and he published a paper in Biometrica in 1908 called The Probable Error of a Mean, which is the basis for the student t-test. Ronald Almeyer Fisher in 1908 was just graduating from Oxford, I think, no, Cambridge at the time. He was a preeminent statistician of his generation, a mathematician, and he saw some errors in Gossett's paper, corrected them using multi-dimensional geometry, sent the results back to Gossett, and used that paper later on in his development of the analysis of variance and the multi-way factorial that was the basis for our work today. So always great to celebrate the contributions of our ancestors, and I'm going to harken back to this later in the talk. All right, so here's an example of an aerial sensor with a set of cursors. We have a target there, and we're interested in estimating the target coordinates. So it looks something like this. There's one of the old Predators. It's still around with its sensor ball there, and it's detecting a target here on the ground. It forms this right triangle here and computes azimuth and elevation, uses a laser to estimate range. So it's sensing this basically in polar coordinates. And most of our weapons now are coordinate seeking weapons. If I give them lat long and elevation, they can guide themselves to that target. So we've got lots and lots of variables in our target battle space. The response variable, the coordinate error between where we think it is and where it actually is, turns out to be skew with an unstable variance. And then we have, as we'll see here, hard to change factors and restrictions on randomization. And sadly, until our brothers and sisters in the Space Force in Area 51 have that transporter working, we're still lacking the ability to randomize. So let's press on. All of these platforms use target coordinates in employing their weapons. And every time we change our operating systems for our aircraft, we have to go back through and revalidate the accuracy of our target coordinate generating mechanisms. All right, so here's a picture. There's another one of our Area 51 platforms that you don't see very much about. Anyway, so as it's sensing coordinates up here over the target and close in, we have some reasonably normal distribution of target errors. But as we move farther away, the variance increases, and as the look down angle gets very, very shallow here, we end up with an ellipse on the ground, and we get a very skewed distribution down in this region. So so it's really a problematic response distribution. And certainly we remember from our trigonometry that the surface of a sphere, which is what these measurements are being made on, is a function of r squared. And so we know it's a quadratic model as well from the physics. And the final thing that makes it really challenging is our response variable is not the mean or the median, but instead we're challenged to estimate the percentiles of the distribution, the most popular being the 90th percentile, to avoid collateral damage. So anyway, but let's focus today on the design issues. All right, so moving forward here, we can use our input process output diagram, or what I like to call the Gazinta-Gazada diagram. On the output side, I have the accuracy of the target coordinates, the target coordinate error over here. On the input side, I've got a whole stack of variables. There's probably 25 of them. I've listed some of the most common ones here. And then God makes life interesting by giving us noise to pack on top of our measurements. makes things interesting in our analysis. So I'm going to look at altitude, ground range, and angle off the nose. These are what I'm going to call the geometric variables. These other kinds of things, which are relatively easy to change, I'm going to call modal variables, and we'll consider the two design problems that they face building those, and then how to bring them together. So moving forward, first we'll deal with geometry and later on the modes. All right, so this is a kind of a geometric picture of altitude versus ground range. We don't bother collecting information down here. Here's a nice linear restriction on these two variables. And the gold standard here would be a perfect randomized controlled trial that we've heard so much about during COVID time. So what we should do is do this: bounce around with our transporter in the design space and take these measurements in a randomized order. But unfortunately, in 2022, we have to occupy the space between these points. So we fly inbound, then back outbound. We drop down to another altitude, fly inbound, go back outbound, and so on and so forth until we finally complete exploring this geometric space and we exit the battle. So that's the way we're kind of constrained by physics to run the problem. So the first thing that jumps to mind is, this is a split plot or a split plot design. And I can handle that with an optimal split plot design. And so when I build one of those, let me jump over here to Design Expert. Let's see, is this the one I want? That's number 5, so no. That's the numeric one. This is a little harder. I thought that I could just alt tab from those things. There we go. Here's a split plot categoric, and you can see I can build that very easily. I'm going to use the same ones to build it. I have, if you watched my talk last year, I talked about the lies that we tell our software. Well, for building this design, if we allowed altitude, range, and some of these other things to be numeric, which they actually are, we end up with an unbalanced design in the numeric variables, and we certainly don't end up with 3 levels of altitude and 4 levels of range unless we get really silly and start building a quintic model to get all of these inflections. So what we found, one of the clever design tricks we use is we tell the software that these are categoric. We go ahead and build the design and let the optimal design work its way through. One of the things I love about Design Expert is that once it's got a solution, you can always cancel out, and it does it reasonably quickly, even on a computer that's not very spiffy. I'm going to stop it here, just in the interest of time. It gives me a pretty good power. It gives me pretty good response, and and I can get the design built there. But as soon as I look at this, I immediately recognize that I've got some serious problems about running this design. I started at 6 furlongs altitude, and look at my ranges. I start at a long range, I move into a short range. Now I need to hover there, take another point, move out to a long range, then all the way back to a short range. And so then I go inbound, outbound, outbound, and outbound. I can't keep going outbound. I have to turn back inbound for every outbound. And so we can see pretty clearly that this optimal split plot is not doing the job for me. It leaves fractional holes because it's a fractional design. We can't hover, and the pilots look at us like we're crazy when we make statements like this. So even though it's a nicely evaluated design, even though it obeys some of our constraints, this really doesn't cut the mustard. So what our design ends up looking like that we can actually fly is altitudes. We start at a long range, move into inbound, then go back outbound, inbound, outbound, change altitudes, and so on and so forth. So this imposes certainly a very restrictive split plot structure. Not only are the factors hard to change, but they're sequential. And I haven't seen that problem in the literature so far. So we needed to solve this. This is ameliorated a little bit by the fact that we understand the physics underlying these sensors pretty well, the electro-optic sensors and the radars. And we can afford several replicates. The points are relatively inexpensive. So at the hard to change factor, we can afford 30, 50, 60, 90 points without a great deal of problems. So second problem after we've run our geometric problems like this, what do we do with the easy to change variables? But before we get to that, let's talk briefly, what coordinate system should we evaluate and build our model in? We have a choice of at least two. One would be the polar coordinates, azimuth, elevation, and range that I originally introduced. And when I first started looking at this problem, I thought the polar coordinates would make the most sense because that's what our sensors think in. But the Cartesian coordinates, altitude and range, with a little bit of a trimmed off corner down here, are also another worthy candidate. So the answer is very easy and very clear when we use design experts design evaluation. So let me see if I can bring that up. There it is. All right. Nope, that's the wrong one. That's it. There it is. This is a DX13 has done some things that I absolutely love. One of them is the ability to import from a cut and paste buffer that I can do from Excel. This one is also very cool. I can right click and ignore a factor. So we can ignore those two and build a model here in altitude and ground range. We could just build a polynomial model just to keep things on the up and up. So when we build that, I get all kinds of great metrics here. I get power, which looks pretty good. A little bit of problem with AB because of that trimmed off corner. The correlation structure looks very nice. There's really no aliases to deal with here. And Pearson's R looks good. The matrix measures are pretty much in good shape. When I go back, on the other hand, and evaluate the other design, let's unignore those and ignore these. I can do that same design evaluation, but this time with CD. And let's do the quadratic again and get the results. And again, very, very quickly, I look at the power on this one, and it, in technical terms, sucks swamp water. When I look at the correlation matrix, I see why. Because this is not nearly an orthogonal design. It's the slant range and depression angle, the polar coordinates, are highly correlated with each other, and the matrix measures are quite terrible. So if I kill that, no, I don't want to save changes. I don't want that. There we go. Here's a summary. There's the Cartesian and polars, power and VIF. VIF, nice and well behaved, down around 1. These are inflated. Power is excellent, with the exception of our two-factor interaction, which we understand from physics belongs in there. The correlation structure for the Cartesian is much better than coordinates. The matrix measures are better. And then looking at the way these things predict, overlaying two fraction of the design space plots, one on top of the other, it's pretty clear that the Cartesian are going to give us better prediction error as well. So that's a slam dunk. Build the models in Cartesian. All right, so let's talk about the easy to change modal variables. So we have things like which sensor frequency do we use, what kind of target type are we aiming at, which side of the aircraft. Hopefully it's symmetric, but it may not be. And then inbound versus outbound direction, and maybe some angles and other kinds of things. There's a whole bunch of these possible easy to change modal variables that we want to change as well. So the history of experimental design gives us some inspiration of how to build the design and the modal variables. We'll remember that blocks form a nearly orthogonal subdesign of the modal variables. And so each individual block we know is a fraction. It's either a classic fraction or an optimal fraction of some sort. And so it encapsulates the design variable model that we're attempting to fit. So that's great. Each little block is a little micro model um, uh, opportunity for us. Back in the 50s, in the 50s, random balance designs were the first attempt to do fractional factorials for the general factorial. Rather than the 2 to the k fractions. We can generate these block designs in the modal variables. The basic geometric inbound outbound run, it consumes about 32 runs. So we can build blocks of around 4 to 8 runs for each block. Those are conveniently sized to fit within our geometric replicates, and we usually replicate our geometric design 2 to 4 times. So here was the idea that we could sequentially roll these nearly orthogonal modal blocks across the geometric design in a Latin square pattern. So I'll go block 1, block 2, block 3, block 4, and then block 3, block 1, block 4, block 2, and so on and so forth. So I've got some history references for you here. Here's a 7x7 Latin square on Fisher's first publication in 1935, where he named this field of endeavor the design of experiments. He had introduced blocks and Latin squares in the 20s and 30s to deal with the fields at Rothamsted, and dealing with blocking designs that were the fertility and drainage and those kinds of characteristics of the field that were not of primary interest to the crop varieties and the fertilization and irrigation and the other kinds of things that were the control variables that he was studying. Satterthwaite introduced this idea of a random balance design, draw a random sample of the multiple levels of usually categoric but also continuous variables, and use those to fractionate the multi-level categoric designs. These have been replaced by optimal fractions, but they were before we had the optimal theory and certainly the optimal generation with this great software that we now have available. Random balance designs were a worthy method for fractionating a large design space and at least getting the main effects right, even though you really couldn't hope to generate at random an orthogonal design in the interactions. And then if those of you have studied using Montgomery's book might remember this little trick in chapter 7, this partial aliasing where I fractionate a design in each replicate, but every replicate I use a different set of fractional generators. So all of these things were bouncing through my mind when we came up with the solution here about 4 years ago. There's our transporter. We don't have that yet, although we're getting good progress reports out of Area 51. But until we get that, we'll use this crossbox routine. So the basic idea is this. I'll take my fixed geometric variables, which are fixed both in sequence, both in hard to change levels and in sequence, flying outbound and inbound and inbound and outbound. And then I'll take and cross those with blocks, nice small size blocks that fit within these replicates reasonably well. And I'll alternate those blocks down through the replicates of the geometric design. So the result will give me a largely orthogonal cross design in the geometric and the modal variables. So let's look into that a little bit more about how we actually do that. All right, so you might remember this table. It's I've been collecting over the years. I've been doing design experiments for, I don't know, 30 some years now. Um, and by the way, shout out to Tom Donnelly if he's out there. Tom's one of the few people I know, and Mark Anderson, who've been doing experimental design longer than I have. But worked with Tom for lots of years. He's a great experimentalist. Just a quick Tom Donnelly story. One of the things he loved to do with experiments was he got very tired of the engineers after the experiment was done of saying, "Oh, well, that's obvious. We knew that going in." And he said, "No, you don't. You didn't think that going in." And so what he took to doing was, as he worked with the experimental experts, is he would ask them to make a prediction about what the results of the experiment will be, write it down on an index card, and sign and date it. And he would take and tuck those in his pocket. And later on, when the experiment was finished, and they said, "Oh, that's obvious. We knew that." He said, "No, you didn't. Here's what you said a month ago or 2 weeks ago or whatever it might be." And I think that's a real hoot. But anyway, so this stuff's been around a while. Cochran and Cox, second edition. The copyright is the year I was born in 1957, had this table in it. If I have a two-level factorial designs in 3, 4, 5, 6, 7 variables, and I want blocks of number of blocks, just say in our case we have 4 variables, I want 4 blocks of size 4, then I would use ABC and ACD as the effects that I give up to generate those 4 blocks. And as a consequence, I'd also lose BD. Well, it turns out Design Expert does a very nice job of generating these 2 to the K blocking designs and giving me control over the block generators. So here's a snapshot. Here's a 2 to the 4th design. I've chosen to do it 4 blocks of size 4 each. And I checked this little checkbox, show generators. I recommend most novices don't do this, but we show the generators. The next dialog comes up and looks like this. The next thing that I tell most novices not to check is check that makes generators editable, but you'll see that they chose AB and ACD to generate these blocks. Is that what was on the previous one? Yeah, 4 blocks of size 4. They used AB and ACD, not quite the same thing. These guys gave up BD, DX gives up AB, ACD, and then their generalized interaction, you multiply those by each other, you get A squared, which is the identity, and BCD. So you give up AB, ACD, and BCD for the 4 blocks. You can change the generators to something with equal aberration and equal resolution if you're careful. So another choice would be give up BC and ABD. Their generalized interaction would be A, B squared, which is I, CD. So you'd also give up the 3-way ACD. You could do CD and ABD, and you give up ABC. So these are what are known as min aberration designs. They use the smallest number of the fewest letters in the generating the design generator or the defining relationship. We give up a single 2-factor interaction and 2 3-ways to generate this blocking design. We should avoid, for example, using AB and ABC, because that generalized interaction would give me A squared, B squared, and C. These were both the identities, so I'd also give up the main effect to C, which sparsity of effects said would be unwise. So anyway, we can build the fractional blocks and use those to roll across our geometric variables. And it looks, you can also do it by hand. I told my students they'd never have to do this, but you can build the same blocking designs by hand by taking a full factorial 2 to the 4th encoded units here, and then choosing a couple of effects to confound with blocks and build 4 blocks of size 4. Take those 4 blocks, mate them up with our back and forth geometric designs to build a whole design of size 96. And we rotate those blocks 1, 2, 3, 4, 2, 3, 4, 1, 3, 4, 1, 2, and so on and so forth across the replicates of the geometric variable. So the overall design looks something like this. Here's the first block, second block, third block, fourth block. I'm done with 16 runs now of my 32 run geometric design. And I could change at this point and go to a different set of generators if I wanted to, or I can just alternate my blocks in a Latin square type fashion here. So anyway, this is the way we build the design. Take the geometric design, made up the blocks in the modal design, and I wanted to show you that. Alt tab. Yeah, so here's a design with modal variables, frequency. If we go back and look at the way I set this up, I want to use the same factors. It says I've got 3 frequencies, 1 and 2. I'm sorry, 2 frequencies, 1 and 2. I've got 2 angles, 0 and 45. I could make those discrete if I didn't want to vary them. That's probably not a bad idea. Let's see what happens if I do that. Make the design problem a little harder for DX. And then tracking modes, if I'm put my cursors and lock on the target, maybe I have 3 different tracking modes, and I'm going against 3 different targets, a goat path, a tiny house, and a Vespa scooter. All right, so I got 3 targets, 3 modes, 2 frequencies, 2 angles, and those are continuous. I can do some things. Here's that little trick I didn't know that Jay just taught me, using the lack of fit as confirmation points. That's cool. I want to have a nice even number. If you remember, I had 32 runs in my geometric variable. So if I go back here, I'd like something that fits nicely in 32. So 24 would do that. Let's see, what have I got here? A 2-factor interaction model, add in 2 additional model points. Now I got a total of 24. If I do that in 3 blocks, it'll give me 3 blocks of size 8 each. I can say next, and then next, and finish. And now this is a way to build blocks if the designs don't come, if the modal variables don't come to you in nice levels of 2, you've got to do an optimal block design. Then I can build this. This is 3 blocks of size 8. I could have gone back just exactly equivalently and done basically however many blocks I'd like. Oops, I didn't want to save that. I do want to go back here. Do I want to use the same one? Save changes? No. I could have done I've got 24 runs. I could have done 4 blocks of size 6, or I could have even gone 6 blocks of size 4, and so on and so forth. So very, very nice blocking control within Design Expert, either for the 2 to the K or for the optimal where I've got mixed level design where I need to fractionate that into blocks. So very nice to have that. So if the modal variables are multi-level categoric or an odd number of levels, then I can optimally block. There's an optimal design 1 for the first set of, looks like 36 runs. I do that again to get to 72. I do that again to get to 96. And I can just run these blocks alternated down the geometric variables till I run out of geometric runs. And we could build a second optimal design and a third optimal design with slightly different blocking structures. There's a correlation for optimal design 1. There's a little bit different correlation for optimal design 2. So again, DX equips me with the tools I need to implement this methodology. All right, we're getting close to the end here. So when I build one of these cross-block designs, the 96 geometric runs, maybe in 3 replicates back and forth across the battle space, another set of modal variables in blocks that I alternate across that, I can import the combined design from Excel to DX and evaluate it with for its correlation and predictive structure. And you see a typical one. Power is excellent, although actually it's not quite that good because we have the restriction on replication that we have with the split plot. So in the 2 primary geometric variables, power is not quite this good. It's more in the 70s region. We've flown these now across many different test ranges here in the United States, more than a couple of dozen times, all kinds of different platforms. The models and the designs work very, very nicely, and the models cross-validate very nicely. So we can use runs that we did use to build our original model, withhold those, build the design without them, and then just like Jay was saying, bring them back in, predict them with the model built without them, and see how well the design predicts the points that it hasn't yet seen. So I found, which one is this? This is a split plot design. This is the one I wanted to show you. So I actually built this one. Here's my geometric design. Here's my modal design over here. I imported it back into Design Expert, and I manually added these grouping variables, which by which Design Expert really means to say whole plots. So I have 24 of these whole plots here, um, which are formed from the altitude primarily, less so at range. And this is actually pretty much an executable design. The only drawback to this is I don't have the capability, or at least I don't know how to do it, to take these 2 things and tell Design Expert the whole plot was generated from using these things. When I go back in to try to tell it that, I don't have that choice. I can't really tell it that this is a whole plot factor, for example. So maybe in DX14 or 15 or 16, we can import a hand-built split plot design and have it analyze it as a split plot. So I don't know how to do that quite yet, but again, the split plot doesn't bother us too much because we have a reasonable amount of replication at the whole plot. We're not likely to make any alpha or beta errors because we understand the physics that drive the model, and altitude and range are certainly 2 of the factors that belong in the model. So almost done. This is my original handwritten notes when I was trying to describe what it was I'd come up with. This is sitting at my desk in January 2018, part of a little short 3-page paper I wrote. I've got 3 replicates in my geometric variables. I fly back and forth for those, rep 1, rep 2, and rep 3. So that takes care of my geometric variables. I'm 32 runs, another 32 to 64, another 32 takes me up to 96 total runs. And then I take my modal variables here, block them in 3 blocks, say, for example, and actually I need 4 blocks. 4 times 8 is 32, according to my calculator. So I need 4 blocks. 3 times 8 is 24, huh? So my notes aren't that good. But anyway, I could take these blocks of size 8 here, roll them across my geometric variables, again in this Latin square type of design, and turns out we get a very nice, reasonably orthogonal, partially aliased structure out of all of that. Okay, so if this interests you at all, then you can actually do this at home. We actually have a lab. We've got, I don't know, 6 or 8 labs that we've developed that we could do in our short courses. And we actually have the students do these different labs. This was, we call our target location area lab. And you can see this gentleman here, who happens to be my handsome son, Daniel, is holding a laser pointer in his hand. And it's interesting that your camera actually dips very nicely into the red color here. You can see the laser spot. He's attempting to aim at where the sound comes from using just his ears as a sensor. He's turned away, so he's only uses one ear for the sound, and he's at about 3 feet height above target and about 10-foot range. So we move those different things. We have a whole bunch of factors that they can vary as part of their planning. They set up their test range here with the distance to the sound source. You could use a cell phone, you could use a laptop, um, and then you actually conduct each of the runs. Here's a very short 6-inch height above target and a good distance away. And again, eyes are closed, as you can see there. And then here's how we acquire the target. We measure the radial distance from the center of the sound source, maybe between the 2 speakers there, to where the point is that they designated on the ground. You can build that into a nice quadratic response surface model and build some lovely little categoric. I'm sorry, these are high quality category 1 coordinates, Cat 2, Cat 3, and Cat 4. That's shorthand we use for the quality of coordinates that are generated by various lasers. So I've got this lab available. It's all written up, looks really nice, and we even have some sound for you. Here's one of them. So anyway, you could use that little sound file as one for them to aim on, and do your own little target location area lab. All right, so we love having Design Expert as a tool. It continues to get better and better every year. The physical world of flight test offers us endless challenges to our creativity, and DX is a great tool that allows us to solve these complex problems that are important for the defense of our nation. All right, so till we get our Star Trek transporter, it's some people would say it's not really a coincidence that the United States Space Force badge looks a lot like the Starfleet badge here. Uh, Maybe we've got some Starfleet equipment out there at Area 51. Not sure, and if I knew, I couldn't tell you. Here's something, Jay, you'll appreciate this. Here's another great quote from both Fisher and his son-in-law, George Box. To call in the statistician after the experiment is conducted is asking him to perform a postmortem. He may be able to say what the experiment died of. I love that quote. It's as true today as it was 100 years ago in 1938 to the Indian Statistical Congress. So anyway, so the summary and target location, we traverse the geometric space, and we do that mated with alternating blocks of our modal design variables. It was a history of experimental design that offered us inspiration for this methodology. The random balance work of Satterthwaite, partial aliasing from Fisher and others that went before him. Euler used Latin squares as well. They're popular in experimentation. They're a great double blocking design. Partial aliasing, I attribute to Doug Montgomery, who introduced it to me. The algorithm is relatively easy to build and repeatable. and the DX tools that we have are critical. It allows us very much flexibility in building custom blocking designs in the modal variables. It allows us to import anything that I can write down and evaluate the excellence of those designs to avoid executing things that have poor modeling structure. And I can say that this design has been confirmed multiple times in actual experiment, and it works reasonably well. So that's all I have for presentation today. I hit 52 minutes by my watch, and I'll take some questions.
That is perfect, Greg. It was just a fascinating presentation, both yours and the previous one from Jay. It's fun to see how these different designs are applied in, solving these real world problems, extremely real world and pertinent problems. So I am querying the audience to see if we have any questions out there.
And yes, I'm aware that I mixed both Star Trek and Star Wars. The Nerf herder was, of course, that was Princess Leia speaking to Han Solo, who said, "I'm not scruffy looking."
All right. Well, it looks like you must have taken care of all the questions with your thorough presentation. I'm not seeing any out there.
Well, that's a part. You wear them out by the end of the thing, and so it's a mixed honor being the last presenter.
Yeah.
But thanks for the opportunity to talk, Sherry. It's
Thank
these
you
things are
so
great.
much, Greg, for being with us.